Very much, Igor. So firstly, thank you for inviting me here. This has been an eye-opening experience, a tremendous meeting. I've really learned a great deal. I'll see how much of it I can actually retain, but it's sort of useful for me. I have a few pictures up here of things that I might get through, and my goal actually is to take you from coupled oscillators to Bose condensates, to flocks, and maybe to neurons, and then maybe back again. So that's a bit of an agenda, and I may not do all of it. But I realize that actually everybody who gives a talk at this meeting has to start with a statement. Right? That's right. Right. Now, actually, I can't make a statement about what is active matter, but I know it when I see it. And also, because I'm a solid-state physicist, I don't like things that move around. Right. So that and that actually is important because I'm mostly going to ignore that. But I hope you can hear this. There's things ticking, right? This is a kind of a famous experiment that many of us do for students, which is to discuss, coupling of oscillators, right? And so here you have two driven nonlinear oscillators. So this is a driven dissipative system. And they're set to the same frequency, but they're actually not beating at the same frequency. They're very close, but they're actually a little bit distinct. If you couple them, and by the way, this is to prove that I'm an experimentalist. You can see, of course, that you can actually enforce synchronization. And it's worth noting that what's happening here is you have a shoebox and two soda cans underneath. And the coupling occurs, of course, because these oscillators are making the shoebox move back and forth. And therefore, there's a tendency for the center of mass to remain fixed. Okay. I am not the first person to have done this experiment. The first person to do this experiment is this guy. Christian Huygens, a much better experimentalist than me because he got a different answer than I just showed you, which I'll explain, and that actually is the purpose of this talk. But he was being paid by the Royal Society on what we would now call a military research grant to design accurate clocks, right? So that the British Navy could travel around the world and understand exactly where they just invaded, right? That was the point, right? Notably, actually, Britain and Holland were at war at this time, right? So he was kind of on the wrong side, and at various points he actually had to decamp to Paris. But he was trying to make accurate clocks, and of course he had a problem because how do you know how accurate your clock is? You could, of course, wait for 24 hours and hope that it's sunny, and not so easy in Northern Europe. Or what he chose to do was to actually build two, on the basis that if you had two clocks, you would try and make them identical. You would know that you couldn't possibly get them to exactly beat at the same time. And therefore there would be a discrepancy, and that discrepancy would give you some idea about how accurate your clock was. He was a bit short of raw materials, so he built them together in the same wooden frame so that they were actually coupled. Okay. And he was surprised to discover that they locked. But interestingly, don't know how good your Latin is. We had a discussion the other evening about some of us were forced to learn Latin at school. Here's an advantage of actually being able to learn Latin. You can read his paper. And while they locked, he noticed that they locked out of phase. So the two oscillators locked this way, right, rather than that way, as I demonstrated. Now, mechanically, we sort of understand that because the coupling here is coming via what we would call phonons, and he noted them. He called it imperceptible movements of the common frame supporting the clock. Okay. So it turns out rather than an inertial coupling, there's an elastic coupling. In that case, you will normally get an out-of-phase locking. Okay? So this, by the way, this is nicely reviewed actually in this lovely research article on this about the history of that. Okay. What I want to talk about actually is almost entirely the transition from in phase to out of phase. So suppose I have a parameter in a model or something I can change in an experiment, which will take me from a regime where I expect to be in phase to a regime where I expect to be out of phase. What would happen? Right? Well, these things are a little bit like ferromagnets and antiferromagnets, if they're a statistical physics problem. So they could go directly. They might go via disordered state, or perhaps they will go via something else. I want to talk about the something else, right? And so in fact, I'll tell you the answer of the talk. And in fact, you heard the answer of the talk because Sabina gave a lovely introduction to this field yesterday. And the answer is, generically, it goes something like this. And let me describe that. What I have on this axis, I have a tuning parameter. And the tuning parameter will take me from something which is phase locked to anti-phase locked. And maybe I can ask what happens as I come from the right. So firstly, in the rotating frame, this is static, so there's no frequency, so I take out the rotating frame. But of course, when I do that, I should remember that if I look at the modes in the system, they have a growth rate, and along this axis up here, there's a Kloster mode, because I don't know the origin of time, and therefore I can shift the origin of time, and therefore there must be one zero mode, to zero the output of this mode. But then there's another mode in the system. If it just has two oscillators, you could call it the clapping mode. So they're actually in phase, which is now in the rotating frame this, and you push them a little bit out of phase. And that will have a restoring force. And that restoring force will produce a damp mode. But it's entirely possible, actually, that damp mode comes to zero in energy. This has a name, it's called an exceptional point. It's a point where, in this 2x2 dynamical system, I have two eigenmodes, and those eigenmodes become identical in the sense that their eigenvectors are parallel and their eigenfrequencies are the same. Of course, this can only happen if the system is not symmetrical and Huygens. Otherwise, you would have no repulsion. But you get to this point where all of a sudden there's no longer a restoring force for this clamping mode. And then what does the system try to do? Well, actually what it does is really chase and run away. So then it slightly moves apart at a very small angle in the rotating frame. And that produces a mode which is chiral. And so there's a chiral symmetry breaking, which occurs here, because this could happen in a left-handed way or a right-handed way. I could have red ahead of blue or blue ahead of red, different frequencies here. And then as I tune all the way across here, these get more or less further and further and further out of phase, until eventually over at this point they come and they lock in the anti-parallel configuration. And there's a second exception. So the transition comes going from a Goldstone mode, a damp mode, which merges with it, to something which has chiral symmetry broken solution. So this is actually very well known in mathematics. There's a long history of thinking about this. What we added to this really is to try and think about a mini-mode system which is doing this, and that's actually what I'm talking about. I said I was going to talk about quantum systems. Here is one, I'll describe it in a moment. But this is experiment which I think is loosely related to this. These authors, in fact, pointed this out. So let me tell you what this is. These are two condensates. They're actually polariton condensates, so you can think of them as bunches of atoms. I'll give you a bit more detail about that in a moment. They're separated in traps, and they're a few microns apart, but they're actually coupled, so they know about each other. And in this regime here, what you might be able to say is you have two sharp spots, and their frequencies are mostly identical, so they're locked. As you're tuning over here, there's some point where they become unlocked, eventually all the way here. But it's worth remembering that this is a time-averaged experiment, so this is happening at optical frequencies. These are condensates, which means that they're oscillating at a very high frequency. It's like a laser. But there's a beat frequency between those two, which you can see. And if you look in this regime, you can see multiple beats. And this is really what's happening when you're taking a snapshot of a frequency cone. So this, and I would say their claim a little bit more than mine actually, is that this represents a phase which is really like that. You can catch up on your sleep now because I've sort of done, at least in terms of the answers, right? So, but now let me take you on a long story and see how far I can get through it. Okay. So the topics I want to talk about is, really, can I think about this as a phase transition? And I'm going to generalize this not from two condensates, but to many condensates, and not from two metronomes to many metronomes, and to try and think about a many-body dynamical system and ask whether you can have some of this in physics. And models and systems like that we actually heard from Sabina yesterday. Is there a critical point in a well-defined system? And does it come decorated with what we call universal fluctuation dynamics? Are there classes of models which are, in some sense, the same in a parallel way to what we're used to in statistical physics of phase transitions? And then the other question is really how quantum can this get? Because I think most of this room is aware that phenomena like this are very common in classical active matter. So it's not a great novelty to do that, right? So, a many-body system? Well, what do I mean by that? I mean something like this. Whoops, I didn't mean to do that. We need to go back. I can't play this for very long. But you could do this with many metronomes. And again, they're all sort of out of sync at the moment. They're coupled on some frame, which at the moment is basically stationary because they're all moving randomly. This is some random phase. And I'm not going to run this for 10 minutes because that would run out my talk. If I go somewhere here, you now see actually that they found a way to synchronize. There's an unhappy one over there. So there's some excitation away from the ground state, which is actually out of phase. Okay. If you're a particle theorist, this is called the Higgs boson. Right. Coherent ground state is suddenly kicked out. That's what it really is. But eventually this one will actually give up and they will all synchronize, and so we're in the synchronized mode. And so let me start with that, because I don't want to run it forever. And then let me introduce the idea of Laraton condensate, because I suspect it's not so well known to many people here. So, but the idea is to quantize that system that I just took you, right? So, what is a quantized metronome? Well, it's a two-level system. I'm going to assume that there's an atom or some semiconductor or something like that, and it can be excited or not excited. So it's either up or down. You can think of it as a spin in some sense. And of course, what excites these things up and down is light. So if I have a bunch of photon modes, these waves, which are living inside a cavity, and I tune the dispersion of these waves so they're very similar to the dispersion of these, I can then mix these modes. And that mixing produces something which is called the Laraton. And in particular, if I've got a two-dimensional cavity, think about something which is planar, then the modes are all confined to the two-dimensional cavity, but there's a momentum in the plane. And then the dispersion of light will look something like this. Excitons, the electron hole pairs, are very heavy. Here they're just dispersionless. A bit of engineering, it's very hard engineering, but thinking how to do this makes them degenerate. And then they couple. And they couple to produce an in-phase and an out-of-phase one. Then the next thing to do is to excite the system and to try and populate these states in the bottom. There are many ways of doing this, but the simplest thing to do is just to add electron hole pairs of high energy and let them scatter their way down and let them more or less thermalize in the bottom of this. And so now you see you've got a dispersive curve. So you've got massive particles sitting in the bottom here. And if it becomes coherent, then you'll actually get a big peak in the dispersion near k equals 0. And that actually will correspond to not just the coherent electron pairs, but also coherent light pair mix. It looks rather like a laser. And if you do that well, then eventually you can look at the light coming out, you can measure the momentum, and you can get this population curve. And so this is something that people have been working on now for about 20 years, and it's a very well-established subject. And in fact, there are lots of things that you can see. So these are pretty good condensates. You can see VC dispersion, you can see the spectrum, W-Hop mode, you can see vortices. Many of these systems are 2D, so you can look at power law correlations, you can do superflow, you can do condensates. But however, it is a driven non-equilibrium system. So there is always energy coming in and there's something leaking out. Okay. So often these systems can get very close to thermal equilibrium, but they're never entirely there. And then you begin to ask the question that we ask, and actually most of this is work done, really led by a postdoc, Rio Hamai, who's now a colleague at IAM in Tokyo, and who noticed actually that, obviously, I've got two modes here. I could make a BEC in the bottom. Maybe because it's non-equilibrium, I can make a BEC in the top. And you say, well, what's the difference between these two? Obviously, they're likely to have different energies. Right? But in terms of broken symmetries, they have the same broken symmetry. They have the same Goldstone mode, the same U1 mode, associated with Bose condensation. And so there's no symmetry distinction between these two things at all. So you should be able to jump between them. Right? And in a way that I'm going from this condensate to that condensate. How would you move that around? Well, probably you're going to tune various parameters in here. But you might imagine as you tune those parameters, there would be some kind of first-order transition, perhaps from one to the other, depending on how you do that. But because it's first-order and there's no symmetry, it's a bit like liquid gas. So liquid gas, no symmetry broken between liquid and gas, and therefore there's a critical point, which is the critical endpoint of this. And here in this system, you'd expect the same critical endpoint. So can one do this? It's a little bit unclear at the moment. You can certainly make condensates in the upper layer. This is some paper from the Stokes group. You can certainly see a transition when you change the pumping rate, where the frequencies jump, so you're crossing that critical line. And you don't always see that, sometimes it's continuous, so we infer that there's something in between. But for the moment, forgive me the theory, and I'll just show you the way that we tend to think about this, which is using a damp-driven Gross-Pediatsky equation with noise and with two components. So here are the photons. There's a loss, so the photons can leak out. Here are the excitons. There's some gain, some pumping. So there's a plus I here. And there's some nonlinear saturation, because this is where the interactions happen in the system. And this G is the Rayleigh splitting as the coupling between the two. And you can play around and tune parameters with that. And you can certainly find in this model and many other related models is indeed, as you change two parameters, in this case, you're changing the damping, and we're changing the pumping, you can find a critical point, and you can find a jump between. Why might this be interesting from the point of view of statistical physics? So the question then you might ask is, this is a mean field theory. So if I look in the vicinity of this point, I should ask, well, what are the fluctuations? Do the fluctuations destroy this? Do they make something else happen? Do they give you some universal scaling? And it's clear it should be different from a conventional phase transition. So here's your standard story of a conventional critical point. You've basically got a Goldstone mode of something going down to the bottom, a massive mode. As a tune close to the critical point, the massive mode becomes flat, and therefore I have a massive mode which vanishes. But here, in a symmetric or mission system, these two modes will always be orthogonal. If you try the same kind of thing towards a critical exceptional point, what happens is that the massive mode actually begins to merge with the phase mode. So there are these two modes which are coming together. So you've now got two Goldstone-like modes, which you can populate. And that, of course, tells you that the fluctuations are expected to be much stronger. And certainly you can show that there's probably no long-range order below 4 dimensions in this problem. We tried to find the upper critical dimension, and we discovered that that was only 8. So although this paper does an 8 minus epsilon expansion, I'm not sure it's terribly helpful. So I'm going to come back to that. So we needed something a little bit simpler, and I'm going to work quickly through this. Some of this you see. So it was clear actually that all of this physics could in principle happen in classical models. Okay? Robots are popular. We didn't have any kilobots. In fact, we could only afford 8 robots. But we decided to program robots so that, we decided to program robots so that they were frustrated. They had asymmetric interactions, sometimes called non-reciprocal interactions. So in particular, we're going to ask them to align, but we give them separate instructions. A wants to align with B, and B wants to anti-align with A. But between their own species, they do this. And then you just set this going, and after you tune the parameters the right way, let's see what the dynamics is producing. If the dynamics indeed is producing this rotation. A few comments actually. If you have a finite number of robots, this stops after a while, at least in the presence of noise. It will only persist forever if there's an infinite number of robots. There is chiral symmetry breaking. Sometimes it goes left, sometimes it goes right. One can extend that idea to kind of models which I think are very well understood here, which are models of flocking. And so here we have 2 kinds of birds. We'll let them flock and anti-flock, and they have similar instructions. And you could just set this going and see what happens. So, with noise, what you're seeing here is something which is dominated by chaos. So the average velocity is 0. Here they flock, here they anti-flock. This is, again, something you saw yesterday in Seeon's nice talk. And in between those, there's something where they chase each other. Now I should say that this is really studied at the big field level, and so there's basically an infinite range interaction. I don't have any fluctuations there, and I now want to talk a little bit about that. But that thing produces the story that I've already told you about, and one can actually generalize it to a whole class of models. Right? So it turns out that these models that I've just been talking about have so-called PT symmetry. I've got an order parameter which is driving you from, on average, up, down to down, up. There's a non-reciprocity system, so thermodynamics is happening along here. There's chiral phases in between. And there are classes of models that do this. Vicek, Turner 2, Swift-Hohenberg, actually, and models of neurons that I'm fond of, Wilson-Cowan. You can have another axis, if you like, which is an axis which breaks the parity time symmetry. Imagine that it's a magnetic field, something like that. And that actually is a class of non-symmetric models, including the Baryton concept that I talked about, and also the remote type models. Let me just say a couple of quick things, because I'm just coming to 25, so I better not go too long. Okay. So I won't be able to answer all of these questions, but I'll show you a few things, and then we can discuss perhaps. Is this stable? But there's 2 ways it could be unstable. One way is that, look, this is a dynamical system. Dynamical systems do weird stuff. And maybe something destroys it. And what's the effect of thermal and quantum noise? So, by the way, if you take Vicek type models, because they're firm, it turns out that you typically, at the critical exceptional point, which would lie underneath here, you typically get flow-induced unstable pattern-forming phases, and this is really associated with the convective term. So the convective term will produce an instability, which will do this. If you go to the polariton compensate models, It's more robust, but my goodness, it gets very complicated. We can see coexisting, we can see a smooth transition, there is a critical exceptional point which can live there, but there are also pattern-forming instabilities, there's oscillatory instabilities going from to chaotic attractors, and there's all kinds of stuff. We thought we wanted to analyze a simpler model with fewer complications. And the one I want to look at is actually 1D. And think about this as a non-reciprocal XY model with noise. So again, I've got spins, A and B. They're given confusing results. I will coarse grain this theory. It will get you to something probably familiar with what you want. And I'll go through this critical exceptional point from a static phase, where they're, say, aligned, to a chiral phase. And then I'll add noise. So this is 1D. So I expect the moment that I add noise, I will destroy the long-range order. How will I measure that destruction of long-range order? I'll typically look at correlation functions and try and do finite size scaling. So, what does that look like? So the standard correlation function to measure is I take the order parameter, I measure the correlation function here in time for a finite system. We expect this to exponentially decay, and it does, and so the susceptibility is really the log of that. And I look for finite size scaling analysis, and here it is. So this is small noise. Here's the critical exceptional point in the absence of noise. Here's the correlation functions, showing that there's a big peak and a divergence. Something, again, I think we saw in Seeon's data. We can now look at finite size scaling. If I look out here, it's traditional. Basically, z equals 2, alpha equals half. As Wilkinson, it's just diffusion. If I go into here, I see something very different. So these are, by the way, these colors are just different sizes. One of the things you see is you see oscillations. And those oscillations tell you that there's a sound mode. So this is the slowest mode to dampen up our system. And so if you choose to scale on that, you're going to see equals 1. But if you wait for them to damp down, eventually it scales with C equals 2, with a much larger exponent. And by the way, this is not KPC, because it couldn't be KPC, because KPC is forbidden by the symmetry of this model. That's one of the reasons I picked it. So that's comparing these 2 points. Another point you might look at is what happens over here. Now, that is going to be more complicated. So here, of course, this is really like an Ising transition. I've got a one-dimensional ferromagnet. I can produce fluctuations of it. I'll produce domain walls, and they will proliferate. If I come over here, I've got a chiral phase. So the unbroken symmetry is, say, rotating right. If I produce a domain which rotates left, then there's a domain wall between right and left rotating, and they will gradually wind each other up. And after they wind each other up, eventually the system will snap, and I will have to form some kind of spatiotemporal vortex. And that actually tends to provoke remarkably order, and I will say we don't understand this, so this is time and space looking at this. We're just looking at the phase of one of the variables, and you can see that there are these lines associated with where the domain wall is formed, and it's pretty persistent. And the domain walls are periodic. It's a spatiotemporal 1+1 vortex pattern. Interestingly, when you look at the scaling, it's not parallel but logarithmic. And I don't understand that. If somebody has an idea of that, I'd love to discuss it. I ought to be done, but let me just... I said I took about quantum systems. You don't need to see this. Right, but a few thoughts about models that one can make quantum. So it turns out that a model that one can construct is very much like the exciton polaritons, but I have 2 species of polaritons. I can think of them as right-handed and left-handed. And I can couple them in a way, this is exactly a polariton Hamiltonian, and I can couple them in a way where I introduce a broken symmetry phase, so that the right-handed one, say m equals 1, couples with +phi, and the left-handed one with m equals -1 couples with -5. So there's a symmetry in this model. It's not quite PT, but it's... So we can analyze this, and we're not the people to introduce this model. It was firstly introduced by these groups, but we looked at it in detail. So it turns out that there's interesting stuff going on here. There's a reciprocal limit where you go from a normal state to a condensate, and then there's a non-reciprocal limit anywhere in between where you can go through these sets of dynamical states. So that's one thing that one can clearly do. Another kind of model that one can introduce is to make a spin chain. Probably the right way to do this is with a Josephson junction array. Here, the way you introduce the non-reciprocity is by having correlated decay associated with, if you like, photons escaping from this site and the neighboring site. And that makes right motion different from left motion. That brings you to something which is well known in the field as the Hartine-Nelson model, but this has a little bit more than that. But the edges are special, so strange things can happen at the edges. And in particular, you could go from regimes where you have no condensate to a condensate, but there's whole regimes where all kinds of awkward stuff happens, right? So I try and describe that in detail. There are different things. But I say these are models that we think are possible to build, but we don't have any experimental data. I'm going to show you this. And lastly, we may, and this is an idea again from my former colleague Rio, which is to do this actually with spins in a ferromagnet, where by pumping at higher levels, you can tune the interactions from one neighbor to another in a non-reciprocal way. So I couldn't go through this in detail, but I advise you to sort of look at it if it's of interest. So here's my conclusion. Sorry for running a bit late. And I will just leave that all there and thank you. And of course, to thank this group, so the people who did this work actually, of course, two very talented postdocs. Michelle is now in Paris, Rio is in Tokyo. My colleague Vincenzo Vitelli, and a number of graduate students. And actually also, I didn't talk about his work, Stefan Wieler, is actually building models of this using neurons. Because one way of making a non-reciprocal model is to have excitatory and inhibitory neurons, because they're explicitly non-reciprocal. And we're trying to work with that. So with that, I really will stop. So thank you very much.
Thank you very much.